Welcome back, student, to this numerical course, numerical analysis, complex analysis course, where this few numerical problem we have done last class regarding the limit and all these things. But before going to that numerical problem, we should start the thing from where we stopped. I mean, fz, this is a complex function. And in last class we mentioned that z is equal to x plus iy is the variable. So, when this variable is changing, x and y should change, and as a result we will have something which is fz, which is a rule. And in W plane we have something this. So, this is a variable, this is not a single variable, this is a dual variable, two variables are associated with that, x and y. And when x and y is related to a rule I called fz, then in the W plane we have another complex number u plus I vx, where u and v are function of x and y. We have shown example and few numerical problems in the last class. We will not going to do any other problems right now. So, next thing was, when the function is defined, we define something limit, say limit x tends to 0 or x tends to some point z0, function of z is L. So, essentially the meaning is, if we have a point z0 here, z is some point which is try to come at this point z0 with a condition that z minus z0 is less than some quantity epsilon, then the function in the function and this whatever the value I have here L, the function try to tends to a value L with the condition that f z minus L mod of that thing should be less than delta. So, this is called the disk or neighborhood of z0, and z is approaching to this point. Here we have something quite different that we have in case of real functions. What is the difference here? In the real case, the approach of some point, say x to x0, is only two way, either it is left hand side or in right hand side. But in this case, in complex case, what happened, we have a region and one can approach to that point z0 any path or from any direction, but the condition is that the limit should exist if it is valid for all the cases. In the last class we show that there are few functions where if I approach from one direction I will have one limit, and if I approach from other direction I will have other limits. So, that means the limit does not exist. So, after having this, so it is an important thing that we need to ensure that in from all approach I will have the same value, and then only we can say the limit exists. Also at the same point I should mention what is the meaning of continuity, where this z tend to z0, if this value is this, then we can say this function fz has a continuity. So, again the limit condition that it should have is the existence of the limit at that particular point, that is the thing. So, here I should mention one important thing, and that is what about the multi-valued function? Okay. Multi-valued function. This is not a very new thing, multi-valued function, because we have already discussed these things in our early class. So, let me give you the example. Say if z is z to the power half this, then what happened if I put z in this way, mod of z and the corresponding phase term which is argument of z, I can write the entire z in this way. So, mod of z is nothing but I just write z in terms of the polar coordinate which is r e to the power I theta. Here r is nothing but the mod of z. So, I just put mod of z here, and e to the power I argument of z is nothing but the theta it have, and big argument suggests that there is a limit of this theta. Now, this limit actually gives something quite different here if I try to find out what is the value of the multi-valued function at certain limit. For example, if I want to find out this limit z tends to say -1, z to the power half. What is the meaning of that? If I draw that in the complex plane, actually which point I am targeting here, where is the limit I want to find? This -1 point. This is real, this is imaginary. I want to go this -1 point, and when I try to find out the limit, that means my approach should be anything from all the direction, whatever I want to approach this, because the condition is that z tends to -1. So, what here I will do that since this is a -1, so this things is nothing but z is 1. I now divide this z tends to -1 this argument to two part. One is the amplitude part, I say z is 1, fine, mod of z, but theta which is the argument tends to pi. That means my one way to approach is something like this. And then if this is the case, the limit is slightly modified here. The function z to the power half I should write in this form. So, then my function, so let me write it here, limit this is equal to 1 and argument which is theta is tends to pi, and this point z to the power half I write mod of z e to the power I theta by 2 mod z to the power half, because here my z is defined in this, z to the power half or root over of z can be defined in this way. Now, if I do that, if I put this limit here, what essentially I am getting, mod of z I can put directly because I am reaching this point with the -1. So, that means mod of z should be 1. So, 1, so it is simply the limit is theta tends to pi e to the power I theta by 2, which is e to the power I pi by 2, which is e to the power I pi by 2 is say I, because cos pi by 2 is 0, sin pi by 2 is 1, I. So, here it is I. Okay, so one approach is something like that, I am going from this to this, I am getting this. Let me try to do the same thing with another path or another approach. So, I will try to find the limit when I am going from this to this. please note that here the direction is changed. So, in the previous case, if I put theta tends to pi, here I should write theta tends to minus pi, because I am going to in the different direction. So, now this limit is modified as mod of z is equal to 1 and theta is approaching to minus pi, because I am going to this point from the other direction. Then z to the power half e to the power I theta by 2. If I put this limit here, you will readily find that it will be e to the power minus I pi by 2, which is minus of I. That means, from this approach the value of the limit is I, and from this approach the value of limit is minus I. So, that means the function, whatever the function is given, if I try to find out the continuity at that particular point, we will find that the continuity is not there, there is a discontinuity. So, that means the function z to the power half has a discontinuity at z equal to minus 1. Now, from here one important thing is emerged in complex analysis, which is called the branch. I will try to cover this in the future class, but not today. In order to understand this branch, you need to know few other things associated with that. So, before that I want you to know the basics of the derivative and all these things, then I will go to this particular thing called branch. Branch is nothing but a multi-valued function should have different set of values. For example, fz is a multi-valued function and for which you have a set of value fi, and this fi is continuous to some limit, and then again after other limit you will again continuous, and after other limit it is again continuous but having the same value. So, then we can say that fi is a branch of these things. For different branch we will have different values, and then if we cut this discontinuity point, we will have something called branch cut. So, this is entirely a subject where you need to spend more time. So, I will do that in the later class when these things will be more familiar to you, but since I am try to make you understand what is the meaning of continuity and all these things. So, at that point you should just I am calculating what is the continuity of these things at that particular point with our knowledge so far, and we find that there is something called multi-valued function, and for this multi-valued function we have this kind of problem of this continuity, and this in that case, since it is a multi-valued, you have a set of values which is same that other set of values in other branches. So, there are different branches which are at some point it is discontinuity, there is a discontinuity between two branches, but you will have a same set of values. So, after having a very rough knowledge about this continuity, limit, all these things, now we are set to define a more important thing, which is the derivative of the complex function. So, the derivative of the complex function derivative of the complex function. So, the derivative is defined as usual. I mean, it is nothing a very, say, what is the meaning of derivative f prime z is essentially the same thing that we have for real case. Delta z is a small increment and the function f z minus function this divided by delta z. This is the standard definition that we have for derivative in real case. Here we are following the same thing. So, fz is nothing but the derivative of a function fz. Fz prime is defined as the derivative, where it is the small increment of the variable z. Delta z is a small change in the variable. This is the original value. So, I want to find out how the function is changed with respect of the change of the variable when the change of variable is tends to 0. For very small change, how the function is changing. Well, here again the same problem arises that we have in case of finding limit and all these things. So, my z here is x plus iy, my z here is x plus iy, delta z should be delta x plus I delta y. This is a variable z which is defined by x plus iy as usual, where x and y both are real quantity. Delta z is a change of the variable. I want to change the variable z, which is defined by this, where the small change of x and small change of y is associated with this change. Fine, no problem with that. Now, if I say delta z tends to 0, that means this entire quantity tends to 0. So, that means which suggests that delta x plus I delta y tends to 0. When delta x plus I delta y tends to 0, that essentially means that delta x tends to 0, delta y tends to 0. So, now the question, same question repeatedly we are encountering, that is, if I say delta z tends to 0 or delta z or z tends to some particular point, what should be my approach here? Here we are having a similar kind of problem. Delta x and delta y both is going to 0. So, I want to find out how, or there are how many ways they can go to 0. So, let us just do a simple thing. So, this is the real and imaginary axis. If I want to go to this 0 point, for example, if I want to go to this 0 point, one approach, last day we actually did it, but still one approach is that I go, this is y and this is my x. One approach might be I can go from this to this, that means delta y tends to 0 and x is equal to 0. That means I put x equal to 0, that means I am not changing this point. So, this point along this the value is already fixed, and now I am saying that the other portion, that means y is going to 0 along this path, so that the point ultimately reaches here some point. In the second case also I can have, okay, my figure is, I need to modify slightly. So, this is my real axis, this is my imaginary, this is y, this is x. Other thing is that I can approach like delta x tends to 0 and delta y is 0. Here I should put delta. So, there the change of y I put 0 and I try to find out what happened when delta x tends to 0. So, x I am approaching along real axis to go to this particular point by changing x, but I am saying that the change of y is already 0. So, delta y is not going to this point. So, delta y is already 0. By the way, there are many other ways, there are, as I mentioned, there are infinite way to approach this point. For example, in general I can also come to any arbitrary direction from here to here, where they can follow this simple relation. Here also delta x tends to 0 gives you delta y tends to 0, but here the thing is I am going to some particular direction depending on the value of n. So, m is nothing but the slope, and I can reaches this point whatever the process or whatever the path I like. But we will stick with these two very specific case to figure out very interesting things. So, let me do that first. Okay. So, I try to find out this quantity, which by definition is change of delta f with respect to z. Okay. Let me write it once again, is limit delta z tends to 0, delta f divided by delta z. It is the same thing that I have written previously. So, it is limit delta z tends to 0, function of z plus delta z minus function of z divided by delta z, function of z plus z, z plus delta z minus function of z, I just put delta f, the change of that thing. Now, f is equal to u plus iv, f of x is equal to u plus iv. So, delta of f is equal to delta of u plus I delta of v. That is the additional thing, because in the previous case, in the previous class what happened, that I defined how the function is changing. If you remember, fz, if I say this is a z square, so z square itself can be represented as x square minus y square plus 2 of I x y, or u of x of y plus I v of x of y, where u of x of y is this quantity and v of x of y is this quantity. Okay. So, now by definition I will have limit delta z tends to 0, delta f is delta u plus I delta v divided by delta z, z is x plus I y, delta of z is delta of x plus I delta of y. Already I use this notation. So, delta of x plus I delta of y. This condition is equivalent to the limit individual delta x tends to 0, delta y tends to 0, delta u plus I delta v divided by delta of x plus I delta of y. After having this, now the question is what should we do, how to go this together. As I mentioned, there are several way to go there. So, the path is according to the choice. If I choose some specific path, I should go with that, but every time I need to check that every time the value, whatever the value I am having, is the same thing. So, keeping that in mind, what I will do, that I will take the two basic paths that I just showed before doing this. That means, one path is, let me write it here, path 1, maybe I can erase this and show that here. Path 1. So, path 1 is what? I say delta x tends to 0, but delta y is 0. I show that. So, if I put this here, then things will be slightly simpler. How? So, then my limit will be only over delta x, because I am saying that delta x tends to 0, but delta y is 0. So, then delta u plus I delta v divided by, since delta y is 0, here there will be no delta y at all. So, I will have only delta x in my hand. These things essentially gives you u over x plus I v of x, where u of x and v of x are nothing but the partial derivative of u with respect to x, because here delta u delta x plus I delta u. So, if I write another step here, it should be, let me write it if you have any confusion over your mind. Under the limit delta x tends to 0, I can write this is del u del x and del v del x, partial derivative because u is a function of x y, but I am taking y as a delta y as a 0 and deriving it with respect to x. So, finally, I have u x plus I v y, where u x is du dx and v x is del v del x by definition. Okay. So, I will have one path, and one path gives me this quantity. I can now choose another path, say path 2, and now I will say that my x delta x is equal to 0, but delta y tends to 0. If I do the same thing, my limit will be simpler. It will be delta y tends to 0, it will be delta u plus I delta v divided by I delta y. From here delta x equal to 0, so this term will be vanished, only thing that we have is this. Now, if I simplify, it will be like 1 by I u of y plus v of x, 1 by y u of y, I will cut out. So, I will have v of x, v of y, where v of y is a partial derivative with respect to y. Now, the thing is that if this is path 1, if the derivative exists, then I must say that the value regarding from whatever I have from path 1 and the end result what we find from path 2 should be same. So, the result from path 1 is same as the result, at least, because I am taking two paths. In principle it should be all the path, but for the two fundamental path, let us try to find out what is this, what is the condition. Results from path 1 is equal to result from path 2. That means this quantity and this quantity are same. So, let me just simply write the equation u x plus I v x has to be equal to minus of I u y plus v y. This minus comes because this I is here, I will just multiply one I and then it come minus I. So, now I know that if two complex quantity are same, then the real part and imaginary part are same. So, if I write this individually, then it will be u x is equal to v y and u y is equal to minus of v x. This is a very important equation. This equation is called the Cauchy Riemann equation. This equation, there is a condition, this is a necessary condition to have a derivative, but not the sufficient condition. This is a necessary condition, but the name of this equation is Cauchy-Riemann equation, in short CR equation. So, today I would like to stop here, but today we did a very important thing in complex analysis. We find what is the meaning of a derivative in complex analysis, and in complex analysis derivative must exist if this Cauchy-Riemann equation is satisfied. So, now this is a necessary condition to have these two things same in order to have the derivative, but important thing is that here whatever we have done is not a complete picture, but we just approach from one side and just check that for these two paths, at least for these two paths, things are same or not. But in the future class we find that this is a very important and very useful relationship between u and v in order to have a function which is which has some derivative in some region, and if a function have a derivative in some region, a particular point say z and a neighborhood of z, then this function has a special name in complex analysis terminology. It is called the analytic function. So, in order to have a analytic function, this condition must satisfy to each other, and with that I will stop here. In the next class we will go with this and try to find out how the analytic function behave and what is the meaning, exact meaning of analytic function, what is the definition and all these things. With this let me stop this class here. See you in the next class, and the next class is important because we will define what is the meaning of analytic function, which is very important in the complex analysis course. With that, see you in the next class.